In this video, we are going to learn about stoichiometry, where we use the stoichiometric coefficients in balanced chemical equations to make predictions about chemical reactions. The coefficients in a balanced chemical equation tell us the ratio or proportion in which substances react. A good analogy is a recipe. A recipe tells us the ratio of ingredients needed to make a certain amount of food. If we want to double the recipe, we must double every ingredient to keep the recipe proportional. Likewise, if we want to cut the recipe in half, we divide every ingredient by 2. Notice that the recipe itself does not tell us how much of each ingredient we actually have. If a recipe calls for 2 eggs, I don't go to the grocery store and buy exactly 2 eggs. I buy a dozen. Likewise, if I need 2 cups of flour, I might purchase a 5-pound bag. I simply store the extra eggs in my fridge and the extra flour in my pantry for later. Balanced equations work the same way. They tell us the proportion in which substances react, but they do not tell us how much of each substance we start with. Chemists and chemical engineers use stoichiometric calculations to predict the quantities of reactants and products needed for a process. This helps reduce waste and avoid purchasing unnecessary amounts of expensive chemicals. These calculations are also useful for small businesses, such as a cottage bakery, where you need to estimate ingredient costs and determine how much product can be made from a given supply of materials. Take a moment to look at the particle diagrams shown here and try to write a balanced chemical equation for the reaction that occurred. In the before picture, we have 6 molecules of hydrogen sulfide and 6 molecules of oxygen gas. In the after picture, we have 4 molecules of water and 4 molecules of sulfur dioxide and 2 molecules of hydrogen sulfide remaining. Notice that the hydrogen sulfide is excess reactant that was left over. It did not react because there was no oxygen remaining. To determine the balanced chemical equation, we subtract the excess hydrogen sulfide from both sides of the comparison. That leaves us with 4H2O plus 6O2 becomes 4H2O plus 4O2. All of the coefficients are even, and balanced chemical equations should always use the lowest whole number coefficients. Dividing every coefficient by 2 gives the balanced equation 2H2S plus 3O2 becomes 2H2O plus 2SO2. Before moving on, let's introduce a few important vocabulary terms. We noticed in this earlier example that we had enough ingredients to do our chemical reaction twice. And we noticed that we had some excess hydrogen sulfide remaining after the reaction. This leftover reactant is called the excess reactant. The reactant that is completely used up first is called the limiting reactant because it limits how much product can be formed. Think about baking cookies. If I run out of eggs, but I still have flour remaining, the flour is the excess reactant, and the eggs are the limiting reactant because I run out of eggs. I cannot make any more cookies. In stoichiometry, we always base our calculations on the limiting reactant because it determines how much product can actually be produced. Our calculated prediction of the maximum amount of product that can be made is called the theoretical yield. Recipes often predict how many servings they make. That prediction is similar to a theoretical yield in chemistry. The coefficients in a balanced chemical equation are called the stoichiometric coefficients. These coefficients allow us to create molar ratios, which relate one substance in the reaction to another. Mole ratios can react a reactant to another reactant, or a reactant to a product, or one product to another product. For example, this balanced chemical equation tells us that 3 moles of O2 reacts with 2 moles of H2S. 3 moles of O2 produces 2 moles of SO2. And for every 2 moles of SO2 that are formed, there are 2 moles of H2O formed. Every stoichiometry calculation begins by selecting an appropriate molar ratio from the balanced chemical equation. From the particle diagram, we know that oxygen is the limiting reactant. Suppose we wanted to know how many moles of H2S are needed to react with 6.25 moles of O2. We begin with our given value, 6.25 moles of O2. From the balanced equation, we know that 3 moles of O2 reacts with 2 moles of H2S. We use this as a conversion factor, arranging it so that moles of O2 cancels, leaving us with moles of H2S. After performing the calculation, we find that 6.25 moles of O2 requires 4.17 moles of H2S. When showing your work, it is extremely important to write both the unit and the chemical substance for every quantity. So doing this helps you correctly orient your conversion factors and avoid common mistakes. We can also calculate how much product forms. Using the same balanced equation, 6.25 moles of O2 produces 4.17 moles of SO2. Here's a practice problem. How many moles of water are formed if 4.17 moles of SO2 are produced? Looking at the balanced equation, 2 moles of SO2 produces 2 moles of H2O. Since the coefficients are equal, the moles are also going to be equal. Therefore, 4.17 moles of SO2 produces 4.17 moles of H2O.